Okay, so before going to links, let's talk about a bit about homomorphisms of monoids in groups. So, because this is one of the most important topics in algebra. And we will have a lot of homomorphisms and isomorphisms in the future as well. Okay. So let X E be a monoid. Oh, sorry. Okay, we have two monoids, so X and Y dot outcome this thing. Okay. I don't know what's symbol to use.
EX and EY.
Okay. X. So this will be star X. Star Y. One bit. We say a function f from x to y is called, such a function is called, sometimes, especially in category 2, they don't put the homo prefix, but so I put it this way. So you can use homomorphism or just morphism. So morphism comes from Greek word morphos, which comes in English is the word form, something that doesn't change form in some sense. It's homomorphism if, so we have two things. First, the identity is respected if f of ex is equal to by, and two, multiplication is respected. So for any a and b in x, we have f of, so we multiply a and b in their source set. So they're multiplied to x, but the result is multiplied by in y. This formula can be written in a diagrammatic way as follows. So I don't know if you need that, but there's an illustration. So we start with a pair, and in that direction we just first multiply it, take multiplication, and arrive at some value at x. And then we take f, go at y. In the other direction, we take separately, we map the first element to y and the second to y. So we just take so-called product of f times f. So f times f. So here I write f times f of ab is a pair f of a, f of b. This is separate forward. This is separate forward. This is just definition. So here, in the first way, we multiply the apply f, and the other way around, we take f's and then multiply them. And then multiply this with y. So that's the idea. No matter how you go from pair of x to y, you get the same result. Okay, so some example. For instance, interesting example is n. Okay, yes. We take integer natural numbers with multiplication with 0, and also natural numbers we can take doesn't matter, with multiplication and 1. And now we are looking for a function. So before I write the function, I'll show what the property is. So we want f. So we are looking for f from n such that for any a and b and n. So in the first part we have addition, so f of a plus b, and in the second part we have multiplication equals f of a times f of b. Can you tell me a function that has this property? Somebody else? I know you told the right solution, but I want to hear from somebody else. Yeah. So any f of the type f of x equals c to the power of x was c is some integer. Even 0 already, because you can take 0 to positive power, so long as it's powers. So we get c to the a plus b equals c times a, c to the power of a times the power of b. This is c, c, c. So you see we have different structures, but we can relate them. I'll be I'm just too lazy to rewrite everything because I now do homomorphism group. So I'll just change these to groups. And here I will put the inverse. So we have two groups now. The group has multiplication, identity, and inverse. And for the groups, we need another one condition more. It turns out that for groups, only one of the three conditions is necessary, but I want to put the whole definition. So, any AX, the inverse of f of the inverse, the f of inverse of x is the same the inverse. Sorry. The inverse A is the same as y. So here the dynamic control from x go by inverse to x and then to y, and here from y so this is the diagram for so this property is the same like before, but we have one more. So we have to keep inverses as well. So the output of the inverse is the inverse of the output in some sense. Okay, here I have only one example. Now, before going, I'm not going to give example and check all the things because it turns out only one thing is necessary. Oh, I forgot in the previous example, C to the 0 was 1, so the 0, the identity of addition is 0, go to the identity of multiplication, which is 1. What are the following proposition? So we have two groups. And y star y groups. And f from x to y is a homomorphism. No. If only if f satisfies two, i.e. Just okay. Condition. So if F satisfies condition 2, then it's a homomorphism. So this means that if you want to check that map is a homomorphism groups, you don't need to check 3 things, we only need to check 1 thing. Satisfies 1 and 3, and so it is a homomorphism. So for monoids, you don't have such a theorem. It's possible to have a map that keeps multiplication but doesn't respect identities. And I will give some example.
If only condition 2 is sufficient,
Yes.
why do you include the other 2 in the definition?
Because there is discipline of mathematics called universal algebra, where you study algebraic structures where all the axioms are given by universal properties. Universal is for all, and there is some equality. And this is specific definition for groups. And my point is that it is the natural definition for homomorphism of group because we have identity in inverse in the structure. And it is a consequence that we only need this condition. But if you define a homomorphism of groups by only giving this condition, a person might think that, oh, so the homomorphism of monoids is again the same thing. But it's possible to have a map of monoids that respects multiplication but doesn't respect identities. That's why I want to have everything included and then show, okay, we don't need everything. You agree? Do you want me to prove that?
If you want to.
Okay. So here we use the fact that we have inverses. So we have that proof. So we first prove f of a, the identity of x equals the identity of y. Indeed, f of ex equals f of ex times ex, which is f of x times f of x. But this time in y. So this thing here, because the identity by identity is itself, and now we use the homomorphism property and we get this. Oh, sorry, this is again. So multiply both sides by f ex to the minus 1. That's the important thing because we are in a group, we have inverses. So we have f of ex to the minus 1 times x equals to y. F x to the minus 1 times f x times x. Now this thing here is identity because we are multiplying versus ey, and this thing here is identity times f of x. And so we have identity is equal to f of x. And this is what we want to prove. You see. And in moments you don't have such a proof. It doesn't work because you don't have inverses by default. And so part 2, we prove that f of the inverse of, let's say, a equals to inverse of f of a. Okay, so we'll multiply this by f of a. So multiply both sides. Okay, so on the right hand we have f of ixa times. Okay, sorry. Yeah. We need to prove that we don't multiply. So we calculate xa times a, f of a. Because it's a homomorphism, we can put the a here. So this will be f of ex of a times a. This is in y, this is in x. What's this? Identity times itself. What is y? This is f of identity of x, which is the identity of y. Similarly, the inverse of f of a multiplied by f of a is ey. This is by definition because this is the inverse. It's an inverse one. So these two things correspond. So we have that this multiplied by something equals this multiplied by something. So f of x times f of a equals I of f of a multiplied by f of a. And we can cancel out because we can multiply by the right inverse here. We can cancel out f of a by multiplying f of a by multiplying on the right by f of a minus the minus 1. And so these things are equal. Okay, I think I made it bit longer than usual, but it's so what?
It's not.
No, it's okay, it's fine. I could make it a little shorter, but I just thought in the wrong way. Anyway, it's the proof is it's fine. It's okay. Okay. So let me give an example of a morphism of monoid. So function that acts like a morphism, but it's not. Example. So both counter example. We have integers, no, yes, positive integers with multiplication 1, and again positive integers with multiplication with 1, and we define f from n to n by, no, this is very good. We define f by f of x equals to 1 on f1 to 0. So we use the constant function. So we use the constant function. So f of x times y is 0. It's always 0. And f of x times f of y is 0 times 0. Is 0 times 0. So this function expects multiplication. However, the identity 1 is mapped to 0. However, f of 1 is equal to 0, which is not 1. So f doesn't expect identity. So f respects multiplication, respects multiplication. But not identities. Do you agree now that it's important to know where something comes from? Yes. Okay. I think usually in books they show this defined homomorphism of groups and then prove that it respects identity and multiplication. But it's a strange definition because if it didn't respect, it wouldn't be a nice property. So my belief is you have to define things right and then show that if you define something in a bit shorter way, it satisfies the properties you desire. Okay. And the most important type of homomorphisms are isomorphisms. I will not talk about it. Okay, let X with some signature and Y with some signature be a monoid or a group. I want to have one definition for both of them. That's why I don't input the signature. So and we say that a homomorphism.
Just a second. Big both monoid and both group or one?
Oh yeah, big monoids. Yeah. Both. So there are two separate definitions that I make into one to be short. We say that a homomorphism f from x to y is an isomorphism if it has an inverse if it's bijective, okay. If it is bijective, usually people stop here because the nice part follows what I will do. And its inverse is also a homomorphism. It's also a homomorphism. So now just put a remark here. Bijectivity is enough, so if it's bijective, its inverse is homomorphism for free. So if it's bijective, it's the inverse is automatically. If you want, you can prove that. So we can prove that if it is a homomorphism, if it's bijective, then its inverse is also a homomorphism. There are situations where, for example, if you study continuous topological spaces, it might happen that a bijection has an inverse that is not continuous. But in groups and monoids, there are not such problems. Automatically homomorphism as well. Example, there are many examples, but I can't think now of a single one that I can show without going too much. So we take x, um, R with addition. That's okay. The rest is determined from addition. Usually people just say the binary operation. I think I said that early in the previous lectures. The identity and the inverse come naturally. And error positive numbers with multiplication. So what is the homomorphism between real numbers with addition and positive real numbers with multiplication? I gave a similar example, before exponent. So f from r plus f of x equals e to the power of x is an isomorphism. And what is it? So its inverse. Its inverse is, of course, logarithmic. Its inverse is logarithm, which is function that takes a real number and positive and takes a real number. So to repeat, so from plus to multiplication, so we have x plus y equals x times y, and we have logarithm of x times y equals logarithm of x plus logarithm of y. And these functions are by ejection. And these functions are by ejections. Those exponents goes from all numbers to positive ones. Okay. So some notation. If two structures are isomorphic, here structures means, for example, groups or moments. Two structures with x and y are isomorphic. We write isomorphic. We write this symbol here. So in the future, I will care about things that are canonically isomorphic, but here I don't need such distinction, but or I will write such thing. X and only one y and then this kind of tilde if it's canonical. This has a precise definition in category 3, but we don't do that. So anytime I have isomorphism, I will use this symbol here. And for instance, we prove that we showed that R plus is isomorphic to R plus the isomorphic groups. So this here is the statement of this. So to be yeah, for things to be isomorphic, there needs to be at least one isomorphism. Okay. I want to talk about things, but I have not much time, so I'll talk about subgroups briefly, because the topic of something to be subspace will be mentioned in the future. So just to lay some foundations. There are, of course, there are submonoids as well, but let me focus on groups. So let G so I can be a group and H is a subset of G. We say that H is a subgroup of G. So in mathematics, people prefer to use some short phrases. G, when you say G, a subgroup of G is not a group. The group is this thing. At least we have to have multiplication, because the set only is not a group. But usually, people, it's known from the context what is the multiplication operation. So H is a subgroup of G if it is a group with the same operations restricted to G. No H, sorry. So we need to have that. So we need three things. So we need, in other words, we need inputs. So first, the product of two elements of H should be in H. If A and B are in H, then A star B is also in H. Two, We need the identity. The identity is also in H. And 3. The inverse is also in H. So if A is in H, then its inverse is also in H. So this. Now, it can be proven that first and third implies 2, 1 and 3 imply 2, and sometimes you can test even simple things. So I'll just write as a remark before giving examples. A remark. It's enough test only 1 and 3. And even, I don't know, something like condition, even a single condition. I think 4, if A and B are in H, then they're A times inverse of B. So you combine multiplication with inverse in a single test. It's also in H. So let me give an example. So take the group Z with addition of 0 and negation as a inverse. And H, let H be, so G equals Z, and H equals NZ. This is the, okay, so this is the set of all multipliers of N. So this is the set. And X, where X is Z. Or this is like 0 plus minus N plus minus 1 and so on. Here I have what is a positive number. No, it's a natural number. Of some N. So this is a subgroup. Why? Well, let me prove it. So this is the set of numbers that are divisible by n. If n is 2, we get the even numbers. If it's 3, we get the numbers divisible by 3. This is the set nz. So indeed, let me take 2 elements. Let A and B are in nz. So that means that, so we need to prove that A minus B. So the inverse is negation, so we need to prove A minus B is also in nz. So we need to prove that if two numbers are divisible by n, the difference is also divisible by n. Well, okay. Let's say equals n times x and b equals n times y, and some x, y, z. This is the definition to be divisible by n. Then a minus b is nx minus na. What do I do with this? Our proof is divisible by n. I use the distributive property. It's nx minus 1. So it's divisible by n. It's divisible by n. Okay. This is another example. This is another example. Okay, you can try this in the meantime if you want. So another example. So let me repeat the general linear group of, let's say, real numbers with multiplication, identity, and inverse. So inverse. This is the general linear group. We talked about this at the moment. And let S, so let, okay, just to recall, so G, L, and L is the set of matrices with the determinant 0. No zero, sorry. And consider the special linear group. Consider S H group with the set so if they go invert the matrix, the not only invertible but the determinant will be 1. And which is called the special linear group. The special linear group. Noted by S L. Okay, let's wrap it up, and if you want, you can take it during the break.